Hello, welcome back to lecture number 4 of the 7th week. In this week, we had already seen Lagrange's mean value theorem, Cauchy mean value theorem, generalized mean value theorem, and related to some of those theorems, we had explored some of the examples. I decided that in this lecture, we will focus more and more on the problems and their solutions so that you cannot confuse and you may enhance your concept where to use the Lagrange mean value theorem, where to use the Cauchy mean value theorem, where to use the general mean value theorem. So let us recall first Lagrange mean value theorem, and it says that let f be a function that fulfills two hypotheses. So f is a real valued function. F is a real valued function from where? From a closed interval a b to r, and such that f of this x is continuous in a closed interval a b and differentiable in an open interval a b. Have you ever wondered why we are left leaving those endpoints for differentiability? I think you may remember that for the endpoints, the differentiability of a function depends of right hand limits, right? So we had here f dash of a. If I want to calculate, then I will realize to find out limit x tends to a plus f of x minus f of a divided by x minus a. That was the definition for that. This definition, this limit does not guarantee its a differentiability in or at that point. So continuity in a closed interval a b does not guarantee the differentiability at that point, at the endpoints. That's why in all the theorems you will see, since it is a critical cases, so endpoints are left. So we had only concentrated on function differentiability in an open interval, not at the endpoints a b, right? And then so we had for Lagrange mean value theorem LMVT, we have a real valued function f from a closed interval a b to r, which is continuous in a closed interval, which is differentiable in an open interval. Then there exists a number c which lying in an open interval a b, or we can say in a closed interval a b but not at the endpoints, such that the slope of the tangent line at the point C can be calculated using the difference between the endpoints of the function divided by the argument difference. That means fb minus fa divided by b minus a. That is the Lagrange mean value theorem. Let me use the different color. This is the Lagrange mean value theorem, right? Similarly, if you remember Cauchy mean value theorem, in which we had used two functions. So let fx and gx be two real valued function. Both are the real valued function. F of x and g of x. From where to where? From ab to r, such that f and g both are continuous in closed interval ab, and this is differentiable in an open interval ab. And the third one says that g dash of x is not equal to 0 in x belongs to ab. So in an open interval, for the endpoints, g dash of x is not equal to 0, is a non-zero. Then there exists at least one c in where? In open interval ab, such that the ratio of f dash c and g dash c, that means the ratio of the slope of tangent lines at point c for a function f and for a function g, can be calculated using the ratio of the difference of the endpoints value of the two functions. That means fb minus fa divided by gb minus ga. So this was the Cauchy mean value theorem, right? This is the Cauchy mean value theorem we call Cauchy mean value theorem, and this is the Cauchy mean value theorem in a general case. The particular case is quite different. And generalized mean value theorem, we have taken three functions, f of x, g of x, h of x in a closed interval ab, and all three functions are continuous in the closed interval ab and differentiable in an open interval ab, right? Then we had defined a matrix d of x that is determinant of x, f of x, g of x, h of x, and their endpoints fa, fb, ga, gb, and ha, hb, right? Then there exists at least one c. One c belongs to an open interval ab such that d dash of c is equal to 0. D dash of c is equal to 0. This is determinant. This is the square matrix. So how to find out? Use those three theorems to solve these examples. These examples explore all those conditions of these theorems. So first one, we change the color first, right? So determine if the mean value theorem can be applied to the following function on the given closed interval. If so, find all possible value of c. Fx is equal to 3 plus root x on 0, 4. So we have given a function and we have given a closed interval. The closed interval is 0 and 4, right? And one function is defined 3 plus root x. So f of x is defined 3 plus root x. Since we have to check that the mean value theorem has been applied at this point or not, let me recall the mean value theorem for you. The Lagrange mean value theorem is valid for one function, and it says that there exists some point c between ab such that the slope of the tangent line at the point c, that means f dash of c, can be calculated, and that is precisely equal to the difference between the functional value at the endpoints divided by their argument, difference of the argument value b minus a, right? So we are going to use, so to use this Lagrange mean value theorem, you have to firstly check whether the function is continuous in the closed interval 0 to 4 or not. If it is not, you cannot use the mean value theorem. Similarly, you have to use mean value theorem. You need to check whether the function fx is differentiable in an open interval 0 to 4. If it is, you will use it, otherwise it's not. So I will check first two things. So 3 plus root x, concentrate on the function 3 plus root x. It is sum of the two function. So 3 is the constant function, 3 is the constant function, root x is a function, right? Now since it is a constant function, it is continuous everywhere. So 3 is continuous in 0, 4, right? 3 is continuous in 0, 4. Now concentrate on root x. Root x is a function, and in 0 to 4 their values lie from 0 to 2 or something, 0 to 2. Therefore, root of x is a continuous function in 0 to 4 as well, right? There is no critical points, there is no discontinuity between these 0 to 4. So that's why it is continuous function in 0 to 4. Now check whether it is a differentiable in an open interval 0 to 4. So what will be the root x? So root of x, let this function f of x is equal to 3 plus root x. So 3 is a constant function. Every constant function is continuous as well as a differentiable in that interval. So that's why 3 is differentiable in 0 to 4. Now root of x. Root of x, what will be the f dash of x? So f dash of x, I can write f dash of x equal to 1 by 2 into root x. This is differentiable everywhere in open interval 0 to 4. It is not differentiable at 4, as you have seen here. It is not differentiable at x equal to 0. So that's why sometime the end points is not valid to include in a mean value theorem. Now this is the one example where you have find that why we are using the function is differentiable in an open interval, not in the closed interval. So this is one example. Since it does not imply that a continuous function in a closed interval may be a differentiable in that closed interval. The end points may be a critical points for differentiability, and henceforth it is expected that the function may not be differentiable at the end points. And that's why in the theorem, the statement of the theorem includes always that a function is differentiable in an open interval AB, not in a closed interval. And this is one of the example, such type of one of the example. So we had seen that this fx now is continuous in a closed interval and differentiable in an open interval in 0, 4. Now we have to find out C point. So let's say C is a point between 0 to 4, which is unknown right now. So we can find out f dash of C. So 1 by 2 into root x, right? And knew that by the mean value theorem, f dash of C is equal to nothing but this is fv minus fa divided by b minus a. And what will be the value of fb? So here 4, so f4. So here f4 minus of f of a is equal to f0 divided by 4 minus 0. So f4 has the value 3 plus of root 4, and this is minus 0. F0 has the 3 plus of 0. So 3 plus of root 0 divided by 4. So this will cancel out 3 to 3, root 4 by 4. So this is equal to 2 by 4 is equal to 1 by 2. So between the points 0 to 4, there is at least one point C here, and C is equal to 1 by 2 such that f dash of C is going to be equal to the function difference of the functional value divided by the argumental value. So that is the validity of the mean value theorem. Now you have understood that differentiability is important in using the mean value theorem. So we have done here f dash of C equal to 1 by root 2, but f dash of C you have calculated here, right? So this is not going to your answer, but instead you have to find out, you have to just put this value. So 1 by 2 root C is equal to f dash of C, and f dash of C is equal to 1 by 2. 1 by 2. So that means C root of C is equal to 1. So C is equal to 1, right? So C is equal to 1 is your answer. C equal to 1 is your answer, not 1 by 2. So now the second one, verify mean value theorem for the function fx equal to x square 4x minus 3 in interval AB where a equal to 1 and b equal to 4. So we have to verify, look at each step for clarity, and fx is given x square minus 4x minus 3. So f dash of x can be calculated 2x minus 4. Therefore f dash of C can be calculated 2c minus 4, right? And C is unknown here, right? Now with the help of this function is sum and difference of three functions. X square is continuous and differentiable, 4x is continuous and differentiable, 3 is a constant function which is continuous and differentiable. That will makes fx is a continuous and differentiable. Can you give one another region that fx is going to be continuous and differentiable? Every polynomial function is a continuous function, and therefore x square minus 4x plus 3 minus 3 is a polynomial, and that polynomial function is continuous in a closed interval 1 to 4. So that's the another reason why you are doing this, why you can tell or why you can claim that this function is continuous in a closed interval 1 to 4 and differentiable in open interval 1 to 4. So f dash of c is equal to, now using the mean value theorem, f dash of c can be calculated as fb minus fa divided by b minus a. So what will be the value of fb? Fb, that means b equal to 4. So that means f4 minus of f of 1 divided by 4 minus 1. f4, what will be the value? f4 is here 16 minus of 12 minus of 3, right? So this is 16 minus of 16 minus of 3 divided by, so this will be comes out to be how much? This will be f4 minus f of 1. This is 1 minus 4 minus 3 and divided by 3. So this will comes out to be here minus 3 and this will be 0. So this will be minus 3 by 3. So this is going to be 3. So this will be going to be minus 3 here. So this is minus 3, 16 cancel out, and here 4 minus 3, minus 4 minus 3 is minus 7 and 1, so minus 6, and minus plus, so 3 plus of 6 divided by 3 is equal to 3 by 3 is equal to 1, right? And this will be given 2c minus 4 equal to f dash of c, and this is equal to 1. So c can be written as 1 plus 4 divided by 2 equal to 5 by 2. That will be your answer. So 5 by 2, where it lies? It's lie 2.5 is here, 5 by 2. So this is the required point where the mean value theorem is valid here. So C is 5 by 2. Now the third example, explain why Lagrange mean value theorem is not applicable to the following function in respective intervals. So in the intervals, here is given minus 1 to 2, this is 1, this is 0, this is 1, right? We have to find out that fx equal to x plus 1 beta x is not applicable in that interval. So firstly, you have to remember what is the Lagrange mean value theorem. Lagrange mean value theorem says that if a function from a closed interval a b to r is defined in such a way that function is continuous in a closed interval a b and open differentiable in an open interval a b, then you can find out the slope of tangent line at the point C such that the functional value difference fb minus fa divided by b minus a is equal, right? So that means I have to prove that this function is continuous in an interval minus 1 to 2. So look at x equal to 0. As x tends to 0, this will become 0, this becomes 0. But what about this one? This one is going to blow up. This one is going to be blow up, which is not a continuous one at 0, right? This is not defined even at x equal to 0, and henceforth it is not a continuous function at x equal to 0. And that means the Lagrange mean value theorem not applicable at this point, right? Now explain why Lagrange theorem is not applicable to the following function in respective interval. So here the interval is given minus 1 to 3, and one function f of x is given 3x plus 1 modulus, and x belongs to minus 1 to 3. And now it says that you have to prove that Lagrange mean value theorem is not applicable for this. That means I have to check firstly function is whether the function is continuous in the closed interval minus 1 to 3 or differentiable in open interval minus 1 to 3 or not, right? So fx minus 1 to 3, so this will give you 3x plus 1 is equal to, at x equal to minus 1 by 3, can you check? So see here. So what we are looking? We are looking for fx is less than 0 or f of x is greater than 0 for some of the interval. So we had divided the interval x equal to minus 1 by 3, and we have here minus 1 by 3, and we have here minus 1 to 3, right? So this implicates that this is minus 1, this is minus 1 by 3, this is 0, this is 1, this is 2, this is 3. So we claimed here that at minus 1 by 3 act like a critical point. So after minus 1 by 3 the function is going to be a positive, and before minus 1 by 3 it is going to be negative. So the opposite behaviors we had, and henceforth the differentiation, can you check whether this claim is true or not? You can check it. Put the value x equal to 0. So what you get? You will get 1, that is greater than 0. Put the value minus 1 itself. What you will get? This is minus 3 plus 1 is equal to minus 2, that is less than 0. So this means here you will get the negative value of the function fx, and here you will get the positive value of the function fx, right? So this is the two behaviors, and henceforth modulus of x, as you can remember that one, modulus of x cannot be differentiable at that point. So that means f of x equal to modulus of 3x plus 1 modulus is not differentiable at the point x equal to minus 1 by 3. And minus 1 by 3, where it lies? It lies in the minus 1 to 3, that means the interval 1 to a to b, and henceforth the Lagrange mean value theorem cannot apply here. Similarly, the next and this is the last question, mean value theorem for the function this one in the interval itna. So we have to verify that this function mean value theorem is applicable for this function, and the function is given 0 to 3, and fx equal to 4x cube minus of 4x. Find out f dash of c. So this will be 12 of c square minus of 4, and we can calculate this one, f of b minus of f of a divided by b minus a. This is equal to how much? 32. Here it is calculated here. So 32, and now equate these two. So 12c square minus 4 is equal to 32, and hence for 12c square minus 4c minus 32 equal to 0. So c is nothing but 1 plus minus of root under 97 by 6, right? And if you do the calculation, your interval is 0 to 3. So only plus will be valid. So c must be 1 plus of root 97 by 6, and this will be your answer. So that means Cauchy-Mann value theorem is valid, and c is equal to how much? The critical c, where the slope is equal to the difference between the functional value and the argumental value, is equal to 1 plus root 97 by 6. So these are the question which were critical, and that's why we had explored the whole solutions. So thank you so much.